Good afternoon, everyone. Welcome back from lunch. I'm Pierre Allier. I'm a senior researcher at INRIA in Sophia Antipolis in France. I will be chairing this session about deformation and registration. And we have a series of 4 talks. And the first one is entitled As Rigid as Possible Regularization for Implicit Surfaces. The authors are Tobias Djuren, Markus Worchel, Hugo Finnendahl, and Marc Alexa, all from TU Berlin. And Tobias is the speaker.
Yeah. Thanks a lot for the introduction. I hope everybody had a great lunch break. Yeah, I give a talk about, did I just reset my timer here? So, I'll give a presentation on as rigid as possible modeling or regularization for implicit surfaces. Yeah, let me directly jump into this. So, as rigid as possible surface modeling is a popular technique for surface modeling, and I think that most of you have already heard of this or used this technique in one or the other way, especially if you participated in the graduate school. So if you take a triangle mesh, as rigid as possible surface modeling, or in short just ARAP, is a method to quickly solve for surface deformation that fulfills a set of often user-defined constraints. So constraints are usually a subset of the vertices, each equipped with a new location in the deformed mesh. And with ARAP, we can then solve for all other vertex positions by assuming a locally as rigid as possible deformation. So ARAP can be described as a method that finds the deformation f, which maps a function f, which maps each vertex to its deformed position. And in recent years, continuous implicit surface representations have become increasingly popular with, thanks to modern learning-based methods. So, yeah, but the original ARAP method was not designed for implicit functions, but for triangle meshes. And in this work, we explain how we can evaluate the continuous ARAP energy in the continuous setting for implicit functions. So our surface is now implicitly given as continuous function that is defined over the entire space, which is R2 in this example, but all of this generalizes well to R3. And while the deformation function f was previously only defined at the vertices, the deformation is now also continuously defined over the surface and again maps each point to its position in the deformed space. So in this setting, this is a variational problem where we try to find the best function f that minimizes the as rigid as possible energy. For discrete ARAP, it was sufficient to store sets of vertices, but in the continuous setting, we need an explicit representation of the deformation f. In the paper, we decided to represent the deformation f using a small network with 4 hidden layers and feature encoding so we can represent high-frequency functions. And in the following, we make use of differentiable quantities of f, so it's required that f is also continuously differentiable. And in practice, this means that we are just using continuous soft plus activation functions for the network. A small note here is that even though we have chosen to represent this deformation f using a network, this is not a strict requirement. So if it's provided that the function is continuously differentiable multiple times, then we can choose other function classes here. The next ingredient that we need are handles that drive the deformation in the continuous setting. And traditionally, constraints are set of points on the initial mesh, as well as the target positions on the deformed mesh. And in our setting, the surface is a continuous implicit function, and we decided to constrain entire regions by using a set of cuboids. So all points inside a cuboid should transform to the corresponding cuboid, those here with the same color, by using the same rigid transformation of the cuboid. And this is inspired by the common approach of constraining multiple neighboring vertices in a mesh for classical ARAP. But we can also map single points of the implicit function if this is desired. So for all points inside the cuboid handles, we already know the deformation function f. So we could choose a simple mean square loss to fit f to these values. For all other points outside the handles, we minimize the as rigid as possible energy. And one of the first continuous interpretations of the Arab energy can be found in the work of Chao et al., even though their main contribution was actually another deformation energy. So this energy is defined as integral over the initial surface S here, and measures the intrinsic stretching and bending when it undergoes the deformation by F. So the first term in the integral measures stretching, and the second, the bending contribution. And both are balanced against each other by the factor which is R squared here. So let me briefly discuss the intuition behind both terms. At each surface point, we can compute the Jacobian of the deformation F, that is the dF here. The Jacobian describes the change of the tangent frame at every point. So for a rigid transformation, the Jacobian is always a rotation. So we compute the rotational part of the Jacobian, which is dr, only the r here, and then we penalize the difference with the Frobenius norm. And for a fully rigid transformation, we also need that the rotation does not change over the surface. Or in other words, for a fully rigid transformation, the deformation tensor of the rotational part dr is 0 at the entries. So here, non-zero entries are penalized by taking the product of dr with itself. And for the original Arab energy, this product is also weighted by the scaling part of the Jacobian here. And there will be another talk directly after me by my colleague Ugo, who will focus in depth on different choices for the Arab bending energy. Okay, so let me first start with the integral over the initial surface before discussing how we handle the stretching and the bending. Okay, so for the surface, to integrate over the initial surface, we use the Monte Carlo approach and estimate the integral by uniformly sampling the initial surface. So here we build on the work of Ling et al., who showed that we can uniformly sample implicit surfaces by casting uniformly sampled rays in the bounding volume, and then find all the intersections of each ray. But computing all intersections of a ray with an implicit surface often results in a highly unbalanced workload on GPUs, especially when we assign each ray to a single thread. So we further improve the performance of their approach by performing load balancing, by splitting the rays, as well as replacing a replacement sampling step in the method. And this roughly leads to a 25 times speed up of the approach. And also know that the Arab energy is defined over the initial surface. So this means that we can pre-compute a set of surface samples, and we think that in many applications, it can be sufficient to just sample a subset of these pre-computed samples during the optimization later. Okay, so given the surface samples, we can compute the stretching and bending contribution at all the sample locations by adapting both terms as a loss function in our setup. And for stretching, we compute the Jacobian at each sample point, and it can be shown that minimizing stretching is equivalent to minimizing the difference of the singular values of the Jacobian to 1. And for bending, we need the derivative tensor of the rotational part R of the Jacobian. And this is the part that describes how the rotation is changing over the surface. So the rotational part is also directly given from the singular value decomposition, that we already computed for the stretching term. So let me briefly show you the effect that these terms actually have on the deformation. So here's a minimal example for a deformed box. And if we only penalize stretching, then the boundaries of the box avoid changing its length, but can still be bended. When we also penalize the bending, then the boundaries form straight lanes as they do in the initial shape. Okay, so here's a brief overview on the entire optimization setup. So we make almost no assumptions on F. In the paper, we choose a small network as a class of functions, but as long as f is multiple times continuously differentiable, we can also pick other function classes. And then this function is then just optimized by gradient descent with the adder method, and we optimize the sampled continuous Arab energy as well as the mean square loss for the constrained regions. At the moment, this is fairly straightforward, but a bit of consideration is needed to compute all the gradients. So the first derivative is needed to compute the Jacobian, and we also need the second derivative to compute the change of the rotation. So the rotation depends on a singular value decomposition of the Jacobian, so we need to compute the gradient of a singular value composition of an automatic gradient computation. I won't go into too much detail here, but in the paper we also demonstrate how we address the stability issues with the gradient here. And finally, for the actual optimization, we also need the gradient of this expression again. But the difference here is that the first two gradients are spatial gradients with respect to the network input, and the third is derivative is with respect to the network parameters. And also note, we focus on implicit surfaces, but this is largely independent of the representation of the surface, and deforming other representations with this setup appears to be straightforward. I have not talked about how we actually extract the deformed implicit surface from the deformation f so far. So in principle, there are more or less two options. So we can compute the deformed surface by discretizing the initial space and then transform the discretized surface, maybe with Worchel cubes, and then transform this result with the function f. This gives a deformed surface, but not the deformed implicit function. So to explicitly extract the implicit function, we need the inverse of f. The deformed implicit function is then given by the composition of the initial implicit function with the inverse of the neural network function f. There are a few invertible neural network architectures, but in our experiments we observed that learning the inverse by training a second network gives much better deformations. And for this we used a simple cycle consistency loss that asks that the composition of f and its inverse is the identity at some samples that are y here, that are sampled at the surface, and a few additional samples in space. So we can then directly compare the results for surfaces that we extracted by both methods, so by deforming the function f and inverse. The initial surface here is on the left side. And for all our examples, we will actually shade the initial surfaces in gray. And then here in the middle, we can extract this surface using Worchel cubes on the initial space and deform the triangle mesh using the network f. This is this result. And here on the very right, when we also learn the inverse function, we can evaluate the implicit surface function directly and compute the surface with Worchel cubes in the deformed space. And usually both surfaces are visually indistinguishable, even though we set our Arab regularization on the function f, which is a good thing. Okay, now let me show some results for implicit surface modeling. So all surfaces are defined by implicit functions, and we constrain and move the regions inside the cuboids. And the speed of the optimization here is the actual speed of the optimization process, except for the surface discretization and the time for rendering in Blender. So we use a simple and relatively lightweight deformation network, as well as pre-computed samples, and then the optimization is sufficiently fast for some interactive editing of implicit surfaces. So here are a few more examples. And also here, so we tested a set of various deformation. Here we twisted the head of the dolphin, but you can also find all these results in the paper. And I think we also made videos for all these deformations on our project repository. But we are not the first who suggest modeling implicit surfaces with the Arab energy. So last year, Bayeri et al. Presented another technique that is very specifically called implicit Arab. So we compare this method to their approach, and they suggest to locally create patch meshes of the implicit surfaces. Then they use these so-generated patches to evaluate a discrete Arab energy. But a limitation of this is that these patches do not strictly reflect the actual surface topology because they are generated using simple nearest point projections. So and in some cases, topologically distant regions are coupled such that they cannot be deformed independently. So here's a simple example where the fingertips are connected by those patches. And even though we only drag one fingertip and constrain the other fingertips, we actually move all of them. And for our regularization term derived from the continuous energy, the evaluation of point samples is sufficient. And this is not only simpler as it avoids having to locally mesh the implicit surface, but also gives direct control on the bending weight. So besides manual modeling with handles, we think that continuous Arab energy is also an easy drop in regularization tool to adapt previous methods to implicit functions. And we demonstrated this for surface stylization. There are multiple methods to stylize meshes for artistic purposes. All of these approaches here define an energy function based on the normals of the mesh, as well as regularize their optimization based on the Arab energy. And in one of them, Kohlbrenner et al. Defined a continuous Gauss stylization loss for stylization, and their preference function assigns weights to the normals of the Gaussian sphere. So the idea is to deform a mesh to match a certain Gauss image. And for cubification, for example, the normals should be aligned with those of a cube. So the only change that we made here to their method was to use the new Arab regularization, which now extends this method to implicit surfaces. And again, here are a few more examples for different sets of normal directions. Those are, the frog uses the normals of a prism, and then we have also like normals of a dodecahedron for the bunny, and an icosahedron for the spot, for the dinosaur. The spot is a cube. And the treaty is an octahedron. Okay. So far, we demonstrated that Arab regularization for a variety of deformations, and we showed exemplarily how this can guide optimization in a surface stylization setting. But there are still some limitations for this approach that should be mentioned. The interpolation of the deformation handles is only a soft constraint, whereas in the original Arab energy, the constraints are perfectly interpolated, and this can only be partially prevented by assigning a higher weight to the constraint loss term. And also, when the initial implicit function is assigned distance function, then the function does not preserve the distance property. And in such cases, we need further reparametrization. We think that regularization with the Arab energy is available too in geometry processing for implicit surfaces that include measuring the deformation between the surfaces. Thanks a lot for your interest. You find all our source code and some Jupyter notebooks to regenerate all these results under this repository. And you can also install everything as a pip, as a PyPy module. Thanks a lot.
Thank you, Tobias. Are there questions for Tobias? Yes, please.
All right, so even though you're measuring the Arab energy on the surface by sampling, does the fact that you're using a neural representation impose some kind of implicit regularization away from the surface as well?
I think we're measuring the actual energy at each point sample and then minimize this with the network. could be that the network, if you don't do the high frequency encoding in the beginning, then you can only represent very coarse deformations, and then you have like bias if you mean this. But
I guess I mean like the model capacity of the network is somehow constrained by the structure of the network, and so I could imagine that that results in some prior on how the deformation should behave even far away from the surface. But I don't know what that would be.
Maybe I'm not sure about this.
Okay.
Yeah.
Thank you.
We had another questions over there.
Hello, thank you for the presentation. I have a question about slide 17, where we can see the animations of the deformations. So those animations are really cool. And I would like to know if at some point the animations stabilize, if the optimizer converge to rest position for the shape, or if it's always shaking?
Yeah, it converges to some point that you see here, but at the end, sometimes it still very little oscillates because we draw random samples and evaluate the energy at some random samples, and I think you could reduce this by drawing a higher number of samples. Yeah, here we choose like a very fast setup so that this runs really fast.
Okay, thank you.
One last question.
So you said the iconal property isn't enforced, and I understand that. I can also buy that for certain applications, maybe that doesn't matter as long as the level set stays zero level set. But do you ever encounter that you get accidentally a different level set far away from the boundary that like ends up showing up if you do Martin cubes or sphere tracing, or is there some argument for like why that shouldn't happen?
Yeah, what we actually do is when we learn the inverse network that we also draw some additional samples in space, and this usually prevents that we also get some results far away from the surface that do not belong to the surface. Give some zero level sets there. Otherwise, you would get this effect, yeah.
Thank you. Let us thank our speaker one more time.